Okay, this video is on z-scores. Now, we've been talking a lot about normally distributed data sets, and we've been drawing a lot of these types of curves, these normally distributed curves. And typically when we draw a normal curve, we note that this point in the middle is the mean of the data set. And then typically we also draw in some standard deviation points. So if I draw in, say, these 2 points here, then this would be one standard deviation above the mean. This is one standard deviation below the mean. And I can draw in 2 standard deviations above the mean, 2 standard deviations below the mean, and so on. Now, so I know that this point right here on my axis, on my scale, that represents one standard deviation away from the mean. Well, I could just kind of estimate, like, this point right here. This point right here is about, looks like it's about a half of a standard deviation above the mean, right? So this point right here, this might be, say, 0.5 standard deviations above the mean. And if I wanted to estimate this point, let's say this point right here, this point looks like it's about 1.5 standard deviations below the mean. So I could call this 1.5 standard deviations below the mean, all right? Well, when I do that, when I start kind of identifying points along the scale here of my normal curve, and when I talk about them in terms of how many standard deviations they are away from the mean, I'm talking about z-scores. A z-score, specifically the z-score of a particular point, a particular data point, is just the number of standard deviations that point is away from the mean. And a z-score can be calculated for any point or any value in a data set. So to calculate the z-score for any particular data point, for any particular value in a data set, there's a formula that we use, z for the z-score. If we take the deviation from the mean and remember, deviation from the mean just means how far away is a particular data point from the mean. And if we divide that distance from the mean, if we divide that by the standard deviation, then that gives us our z-score. Often you see this formula written as, since the deviation from the mean, remember, means you take the value of the data point and you subtract the mean. That gives you the deviation from the mean. So data point minus mean divided by standard deviation. And that gives you the z-score for that particular point. So let's take a look at how we would go about calculating some z-scores. Example number 1 says a group of students weighs 500 US pennies. They find that the pennies have a normally distributed weights with a mean of 3.1 grams and a standard deviation of 0.14 grams. So this is the same example, same situation that we had in some previous examples. I've got a bunch of pennies. The mean weight is 3.1 grams, and the standard deviation is 0.14, the standard deviation of all of my pennies. So what is the z-score then for a penny that weighs 3.24 grams? Well, I have my z-score formula here. The z-score formula just says the value of the data point minus the mean divided by the standard deviation. Well, the data point that I'm interested in is this value right here, the weight of this particular penny. So that's 3.24 minus the mean. I'm told the mean is 3.1 divided by the standard deviation, which is 0.14. And now I just have a little bit of arithmetic to do. 3.24 minus 3.1 is 0.14 divided by 0.14, and that's going to equal to 1. So the z-score for a penny that weighs 3.24 grams is 1. That tells me that a penny that weighs 3.24 grams is exactly 1 standard deviation above the mean. What's the z-score for a penny that weighs 2.96 grams? Well, again, I'm going to use my same formula. Now I'm going to plug in this value for my data point. So that's going to be, my z-score is going to be 2.96 minus the mean. The mean is 3.1 divided by the standard deviation, which is 0.14. And I do a little bit of arithmetic. See, 2.96 minus 3.1 gives me negative 0.14 divided by 0.14. And so the z-score for a penny that weighs 2.96 is negative 0.1. And this again tells me that it's 1 standard deviation away from the mean, except in this case it's 1 standard deviation below the mean. What's the z-score for a penny that weighs 3.31? Plug into my formula here, 3.31 minus the mean, which is 3.1, divided by 0.14, and that's going to give me 0.21 divided by 0.14, and that gives me a z-score of 1.5. Z-score for a penny that weighs 2.89. Z equals 2.89 minus the mean, 3.1, divided by the standard deviation, 0.14. And let's see, that's going to be negative 0.21 over 0.14, which is negative 1.5. So you can see a positive z-score just indicates that the data point lies above the mean. And a negative z-score just indicates that the data point lies below the mean. And then the magnitude of the z-score indicates how many standard deviations that point is away from the mean. Okay, example number 2. It says for the same data set in example 1, if a penny has a z-score of 0.64, how much does it weigh? Okay, so we've got our same data set that we had before. Our pennies have a mean weight of 3.1, a standard deviation of 0.14. This time, however, we're given the z-score and we're asked to come up with the weight of the penny. Well, we're going to be using the same formula that we used before, our z-score formula. Z is the value of the data point minus the mean divided by the standard deviation. Well, in this case, I know the value of my z-score, so I can go ahead and plug that in here. So my z-score is 0.64. So z equals the data point. This is the thing that I'm looking for. My data point is the weight of my penny. So let me call that x minus the mean. My mean is 3.1. And my standard deviation is 0.14. So you can see we now have an equation here. I've got an unknown that I'm trying to solve for. That unknown is my data point, which is the weight of my penny. All I need to do is solve that equation for x, and I'll have the weight of a penny whose z-score is 0.64. Now I'm going to leave this for you to work out and find out what the weight of that penny is. And I'm also going to leave part B here for you to figure out. It's essentially the same calculation, just a different z-score. So I'll leave that for you, and we'll take a look at these examples in class tomorrow.